Now what about this reaction? We have a permanganate ion and it's reacting with, what is this? Anybody remember? H2O2, hydrogen peroxide. And together they yield manganese 2 ion and just oxygen gas. So let's go for it. Let's dive in. Well, each of these oxygens has a -2 charge. Overall, -8. Notice we have a net of -1. So therefore this manganese needs to be a +7. Okay, now look at hydrogen peroxide. If you'll recall, this is a situation where oxygen doesn't have the typical -2 charge. This time, each oxygen has a -1 because there are 2 of them. And each of these hydrogens has a +1 charge. Okay, focus on the products. We have manganese 2, so it's just a +2. And then now we have oxygen gas. If you remember, your diatomic molecules have an oxidation number of 0. Okay, let's identify what occurred. What happened to which element? So if we focus on the manganese, we go from a +7 to a +2. We became less positive. The only way that that could happen is if we accept electrons, right? i.e. get reduced. We got reduced right here. Okay. Now, notice here we have an oxygen with a -2, and over here it's 0, but you have to remember that redox reactions is really like a coupling or a coupled reaction, meaning one chemical constituent or chemical compound is going to get oxidized, while some other chemical compound is going to get reduced. Okay, so we're not going to focus on that oxygen right now because it's part of the chemical species that got reduced. We need to focus our attention on the hydrogen peroxide. So what happened? We go from -1 to 0. So electrons were stripped away. Therefore, it was oxidized or oxidation. Oxidation occurred, okay? All right, so let's go for our reduction, half reaction. Reduction, and over here we will do our oxidation when we get to it. Okay, let's go for it. Permanganate ion. And we ended up just getting manganese 2. Manganese 2 ion. Step number 1, make sure that the manganese is balanced, and it is. So now we're ready to focus on the charges. Which manganese was more positive? Obviously +7. We need to bring it down to a +2 level by adding 5 electrons. Okay? Now we're ready to focus on the oxygens. Notice that there's 4 oxygens here. So what does that mean? It means that we need to add 4 waters to the right side of the reaction. Now 2 times 4 hydrogens is 8. So we need 8 hydrogen ions, 5 electrons, the permanganate ion, to yield the manganese 2 ion and the 4 waters. Okay, that half reaction is done. Now for the oxidation. We go from H2O2 to just oxygen gas, okay? And notice that the oxygens are balanced. And we want to go to the side that is more positive, and technically 0 is more positive than -1. So how many electrons do we need to add here? Just 2 electrons, okay? Good. Now, what about the oxygens? The oxygens are balanced now. What about the hydrogens? 2 hydrogens. We need to add 2 hydrogen ions to this side of our reaction. And now we're ready to consolidate. So let's bring it down. And I'll set it off so it's easier on your eyes. And we'll say hydrogen peroxide yields oxygen gas plus 2 electrons plus 2 hydrogen ions. And then over here, 8 hydrogen ions plus 5 electrons plus the permanganate ion yields manganese 2 plus 4 water. Okay, focus on the electrons. We need a common multiple. So up here, we're going to need to distribute 5. And down here, we need to distribute a 2. Okay, let's go for it. So I'll do it like this. I'll set this off again. Okay, it's all about compartmentalization. 5 hydrogen peroxide, 5 oxygen, 10 electrons, and 10 hydrogen ions, okay? Down here, 16 hydrogen ions, 10 electrons, 2 paramanganate ions, 2 manganese 2 ions, and then 2 times 4 is 8 waters. Awesome. We're ready to start canceling. Let's do our electrons. 10 cancels 10 electrons. Good. Now focus on the hydrogen ions, let's say. Here we have 16, here we have 10. All 10 of those are going to cancel, and we're left with 6 remaining hydrogen ions. Now, are there any waters for us to cancel? We only have waters participating in our reduction reaction and not in the oxidation, so we can't cancel any of those. So we're ready to actually consolidate at this point. Let's do it. So 5 hydrogen peroxide plus 6 hydrogen ions plus 2 paramanganate ions yields 5 oxygens plus 2 manganese 2 ions plus the 8 waters. Okay, let's make sure we're balanced in total here. Start with your metal, 2 manganese, okay? Now for the non-metals, well, we just have hydrogens and oxygens. At this point, 2 times 5 is 10, plus the 6 is 16, and over here we have 2 times 8 is 16, hydrogen's okay. Now for the oxygen, 2 times 5 is 10, plus 4 times 2 is 18 in total, and then we have 2 times 5 is 10, plus 8, again 18. This redox reaction is balanced now. Okay, for this reaction we have hydrobromic acid reacting with sulfate ion to yield sulfur dioxide and bromine gas. You know the process. Bromine's group 7, so -1. Hydrogen's +1. Here in the sulfate, each oxygen is -2. So overall, a -8. Now notice we have a net of -2. So that means that this sulfur has to be a +6. Over here, this oxygen would be -2 for a total of -4. So that means that the sulfur is +4 here. Notice bromine is a diatomic molecule, right? So recall, diatomic molecules have an oxidation number of 0. Okay, what happened? Do you see it already? Let's skip the hydrogen. How about the bromine? What happened to it? It went from -1 to 0. It became more positive. Electrons were stripped away. So therefore, this guy got oxidized. Oxidized, okay? Now what happened to the sulfur? It went from +6 to +4. It became less positive. So therefore, it got reduced. This time, let's go after the oxidation half reaction first. So we know we have hydrobromic acid, and it ended up yielding bromine gas, okay? So, number 1, are the bromines balanced? Absolutely not. We do need a coefficient of 2 over here, okay? The next step, it's all about getting them to the same type of charge. You want to add electrons to the side that is more positive than the other. Obviously, 0 is more positive than -1. So what do we need to do? Well, we need to add electrons. How many is the question? Exactly. 2 electrons. Now think about that for a second, right? 2 electrons to the side, because why? Now we have 2 bromines, and each bromine brought to the table a -1 charge. Now it's overall -2, so that's what we have to have. Now since there aren't any oxygens, we can go right to the hydrogens in this reaction. Notice there are 2 here, so what do we need to add? We need to add 2 hydrogen ions to the right side of the reaction, okay? And overall, that one's done. Let's go for our reduction half reaction. Reduction. Okay, what happened? Well, we had sulfate ion, and it ended up producing sulfur dioxide. All right, are the sulfurs balanced? The answer is yes. Okay, what about the charges? Which is more positive? Obviously, positive 6 is greater than positive 4, so we need to add 2 electrons to this side. Okay, and now let's focus on the oxygens. Notice we have 4 on the left side of the arrow. Here we only have 2. So we need to add 2 waters. And in doing so, we've actually added hydrogens at this point. So 2 times 2 is 4 hydrogens. We need 4 hydrogen ions here on the left side. SO4 minus 2, sulfur dioxide plus 2 water. Okay, let's get them side by side. And I'll set it off here. Actually, you know what? I can just do that, and I'll bring this one down. Okay, 2 hydrobromic acids yielding bromine gas plus 2 electrons plus 2 hydrogen ions, and that's it. 2 hydrogen ions, good. All right, now focus on the electrons. Do we need to multiply them by any type of value to get a lowest common multiple? And the answer is no, because it's 2 electrons. We're actually ready, we're skipping that step and going right to the canceling process. So these 2 electrons are going to cancel those 2. Great. All right, now what about waters? Only this reaction had waters, not the oxidation reaction. Okay? What about hydrogen ions? Absolutely. We can cancel those 2, and then we can get rid of the 4, and we're left with 2 hydrogen ions. Now we're ready to consolidate. Okay, do we need to bring anything down? No, we didn't leave any spectators for later. We didn't leave any, so we're good. Let's balance or ensure that our redox reaction is actually balanced. Here we go. Any metals? No, not this time. All right, how about nonmetals? You bet. 1 sulfur, 1 sulfur. Here we have 2 bromine. Here we have 2 bromine. Now we're ready for the hydrogens. We have 2 plus 2 is 4. And oh, here on the other side, 2 times 2 is 4. That's balanced. Now for the oxygens. Here we have 4. And over here we have 2. And then don't forget this 2 distributes to that oxygen. So 2 plus 2 is 4. This redox reaction is now balanced. All right, now what about this reaction? We have bromate ion plus iron 2 to yield a bromide ion and iron 3. So let's figure out our oxidation numbers. Each of these oxygens is -2 for an overall -6. Notice we have a net of -1. So this bromine, which is somewhat unusual from what we're accustomed to, this one would be +5. All right? This is just iron 2 with a +2. And then this is the bromide ion with an overall -1 charge. And then iron 3. Okay, what happened? You could see what happened to the bromine. Something happened. It was positive and became negative. It gained electrons. So therefore, it is reduced. Reduction happened, okay? Oxygen will skip. Now what about the iron? It was a +2 and then became +3. It lost electrons and therefore got oxidized. Okay, so let's do our bromate first, which is the reduction. Say reduction, half reaction. Okay, here we go. We'll say our bromate ion yields bromide ion. Check to make sure that your bromines are balanced, and they are. Now we need to add electrons. Which side is more positive? Obviously this side, +5. How many electrons do we need to add in order to bring it to -1? Well, the answer is +6. 6 electrons. 6 electrons need to be added to that side. Now focus on the oxygens. 3 oxygens, so we need to add 3 waters. But now we've added hydrogens to the situation, and actually it's a total of 6, So we're going to say 6 hydrogen ions plus 6 electrons plus the bromate ion yields the bromide ion plus 3 waters. Okay? That half reaction is done. Now for the oxidation. Oxidation. Here we go. What happened here? Well, it's just iron, and I'll do it in purple. Iron with a positive 2 charge ended up becoming iron with a positive 3. Okay, are the ions balanced? Yes, they are. Now for their charges, which is more positive? Obviously that one, how many electrons do we need to add? Just 1. 1 electron, okay? No oxygens, no hydrogens. We're ready to start the process of canceling and then ultimately leading on to consolidation. So let's do it. I'll go ahead and set it off and rewrite it. So let's go. Iron 2 yields iron 3 plus the 1 electron. Okay, over here we have 6 hydrogen ions plus 6 electrons plus the bromate ion yielding the bromide ion and 3 water. Okay, let's focus on the electrons. Here we have 6, here we have 1. All we need to do is distribute 6 across the board, across this whole half reaction. So I'm going to write it, here I'll set it off, since we won't be using that one anymore. I'll bring it down here. 6 iron 2s yields 6 iron 3s plus 6 electrons. Now we're ready to start canceling. The 6 electrons are going to cancel one another. Any waters that balance out? No. Any hydrogen ions that balance out? No. So let's go ahead and consolidate now. We'll do it, here we go. I'll say 6 hydrogen ions plus the bromate ion plus 6 iron 2 ions yields bromide ion plus 3 water plus 6 iron 3s. Okay. Any spectators that we need to bring down? Nope. We have all the constituents from the original reaction. Last step, guys, balance. Make sure everything's balanced. Okay, start with the metals. 6 iron. 6 iron. Next, the bromine. 1 bromine, 1 bromine. Okay? Now for the hydrogen. 6 hydrogen. 2 times 3 is 6. And lastly, the oxygen. 3. That's it over here. And as you can see, the 3 distributes to that oxygen, so it's 3. This half reaction is balanced. Okay, now we have elemental zinc, and it's reacting with nitrate ion to produce ammonium ion and zinc 2. Okay, so since this is just an element, its oxidation number would be 0. You remember that? And then for the nitrate ion, remember each of these oxygens brings a -2 to the table. There are 3 of them for an overall -6. Notice the net of the polyatomic ion is -1. So therefore the nitrogen has to be a +5. Okay, coming over here, now it's kind of a different situation. I'll start with the zinc. Obviously this is zinc 2. Now with ammonium, ammonium's a little bit different. Each of these hydrogens, like the order, the hydrogens are going to be +1. There are 4 of them. Notice we have a net of a +1 charge. So what does that tell us about the nitrogen? It tells us that the nitrogen needs to be a -3, which is pretty typical, but I know it's odd seeing them out of order, kind of, right? Okay, now identify what happened here. What happened to our zinc? It became more positive. So therefore electrons were stripped away, and we say that it was oxidized. Okay, what happened to nitrogen? Here is +5, and all of a sudden, it's now -3? Wow, it gained a bunch of electrons, right? So, how many electrons? Quite a few. We say that it got reduced. Awesome. Now, let's break it up. And let's go after the oxidation first. Oxidation. So we have zinc, elemental zinc, and yielding zinc 2 ion. Which side is more positive? Obviously the positive 2. How many electrons should we add? Well, we need to add 2 electrons. Just 2 electrons to this side, okay? Anything else that we need to do? The answer is no. And guys, I'm sorry, I didn't kind of pump the brakes a little bit and say, okay, are the zincs balanced? Yes, they are. So you can't forget about that step. But I had already assessed that in my mind and quickly jumped to the next step. So anyways, there it is. No more oxygen, so we can't add any waters or hydrogen ions. Let's go after the reduction reaction. Reduction. And we had nitrate ion, and ended up yielding ammonium ion. Well, are the nitrogens balanced? Yes, they are, so that's good. Now we can actually focus on which side is more positive. Obviously this. So if we add 5 electrons to this side, we're bringing it down to 0, right? How many more do we need to add in order to get to -3? Just 3 more. So we're looking at a total of 8 electrons that need to be added to the left side of the half reaction arrow. Are y'all with me on that? Good. Okay, what's next? Exactly, focus on the oxygens. Here we have 3, so let's add waters. Let's add 3 waters to the right side. Okay, how many hydrogens are on this side? 2 times 3 is 6, but don't forget we have 4 additional ones from the ammonium ion, so a total of 10. We need 10 hydrogen ions plus 8 electrons plus the nitrate to yield the ammonium ion and the 3 waters. Okay? Now, I'm just going to bring this reaction underneath here. Zinc to yield zinc 2 and the 2 electrons. Now look at the electrons. We need a common multiple. We can easily turn 2 into 8. And the way that we'll distribute that is we need to multiply everything by 4. So we'll have 4 zinc. We'll have 4 zinc 2 ions. We'll have 8 electrons. And I'll go ahead and bring this one down as well. 10 hydrogen ions plus 8 electrons plus the nitrate to yield the ammonium ion and the 3 waters. Okay? Awesome. Let's go ahead and cancel our electrons. 8 cancels 8. Anything else we can cancel? How about waters? And the answer is no, because in our oxidation reaction, we didn't have any water. So we're actually at the point where we can consolidate the entire reaction. So let's do that. I'm going to say 4 zinc, because we didn't have any spectators to bring down or anything like that. 4 zinc plus 10 hydrogen ions plus the nitrate ion yield 4 zinc 2 ions plus the ammonium ion and the 3 waters. Okay, last step. Making sure that we've obeyed the law of conservation of matter. And so we have 4 zinc on the left, 4 zinc on the right. Now for the nonmetals. 1 nitrogen on the left, 1 nitrogen here on the right. And now for the hydrogens, we have 10 here on the left side. And then notice we have 2 times 3 is 6, plus 4 is 10. Hydrogens are taken care of. Now for the oxygens, 3 oxygens. And this 3 distributes to that oxygen, so that one's balanced. The whole redox reaction is balanced at this point. Now here's an interesting reaction. We have dichromate ion and then some type of organic compound here, the C2H4O, and it yields acetic acid and chromium 3 ion. I'm going to warn you guys, this particular compound, this acetic acid, it's a little bit difficult to determine the oxidation numbers. We'll come to that in a second. So each oxygen here is -2. Notice that there are 7, so overall it'd be -14. Notice there's a net of 2, so that means that these chromiums contribute a total of +12. You with me? But there are 2 chromiums, right? So each chromium brings to the table a +6 charge. Now for this compound, it's a little bit interesting. The oxygen is -2. Each hydrogen is +1. So if we examine the whole, or the charges on the whole compound, the hydrogens bring a +4 to the table. The singular oxygen is -2. So what does that say about the carbons? The carbons bring a -2 charge to the table, so we can neutralize. Since there are 2 carbons, each one brings a -1. Kind of interesting. Okay, here's the one I was talking about, the acetic acid. It's kind of a little bit funky, if you will. Each of the oxygens is a -2, and notice we have a total of 4 hydrogens, right? And so it's 4, the +4 charge on the hydrogens cancels out the -4 charge on the oxygens. So what does that say about the oxidation number on the carbons? Well, you know, the carbons, they could be 0, they could be equal but opposite, like where one's a positive and the other's a negative. Don't really know. So I'm going to kind of leave that blank right now. What about the chromium 3? Well, that one's easy. Very transparent. It's just +3. Okay, can we determine what happened in this reaction? What happened to the chromium? It went from +6 and became less positive. So therefore electrons were added, and therefore it got reduced. So reduction happened here. All right, what else? Since I'm uncertain about the actual carbons, we can really just focus on the compound as a whole. We know, again, redox is a coupling process. One compound gets reduced while the other compound gets oxidized. Or actually, I should say it the other way around. A compound gets oxidized, loses its electrons, while the other compound receives those electrons and becomes reduced, okay? So we know that the whole compound here, this whole thing, got oxidized in the reaction. So oxidized. Are you with me on that thinking? Sometimes you have to go a little bit broader instead of just focusing on the individual oxidation numbers. Okay, so now let's do our reduction half reaction over here. Reduction. Okay, what happened? The dichromate ion got reduced and became chromium with a +3. We got to make sure that the chromiums are balanced, right? Well, right now they're not. Here we have 2, here we have 1, so let's put a coefficient there. Now they're balanced. Okay, which chromium is more positive? The +3 or the +6? Clearly it's over here. Now remember, there's 2 chromiums, so we need to add a total of 6 electrons, right? Each chromium gets 3 electrons in order to get to that level. Of that level of oxidation number, having the +3. Okay, what else? Notice 7 oxygen. Well, let's add 7 water. But in doing so, we've added hydrogens at 14. So let's add 14 hydrogen ions to this side. 6 electrons, the dichromate ion, 2 chromium 3s, and 7 water. Okay, that's our reduction reaction. Let's go for the oxidation. Oxidation. So if we look at the whole molecule here, C2H4O to form acetic acid. So really we're focusing on the carbon here, right? I mean, it kind of makes sense because we'll handle the oxygens and the hydrogens in a different fashion. So what happened? Well, are the carbons balanced? Technically they are, because there's 2, and then over here there's 2. So since there were 2 electrons, we do want to go after the one that's more positive. So I'm going to go ahead and commit, guys. I'm going to go ahead and say that somehow these carbons, they don't bring any oxidation number to the table. They're just 0. So now they're the more positive compound. That being the case, we're going to add electrons to this side. Well, the question is how many? Well, it needs to be 2 because we had 2 carbons. Each carbon had an oxidation number of -1. So 2 electrons will be added. Okay, we're on our way. Now let's focus on the oxygens. We had 2 over here and just 1 on the left side of the arrow. So we need 1 more water. We'll say H2O plus C2H4O yields the acetic acid plus the 2 electrons, okay? Now the oxygens are balanced. What about the hydrogens? Over here, we have 3 plus 1 is 4, and then over here we have 2 plus 4 is actually going to be 6. That's a problem. So what do we need to do? We need to add 2 hydrogen ions, 2 of them, to the right side of this half reaction. Now, in order to have some economy of space here on the board, let's just go ahead and look at our electrons and figure out the lowest common multiple. Here we have 2 electrons, here we have 6. We can easily turn this into 6 electrons by multiplying the whole thing by 3. So let's go for it. 3 water plus 3 C2H4O yields 3 acetic acids, the 6 electrons that we were after, and 6 hydrogen ions. Okay, cool. And again, for economy of the board, I'm just going to do the next step here with the reactions where they are, okay? Let's cancel the electrons. 6 electrons is going to cancel these 6 electrons. Now waters. They both have waters. We can actually cancel some water. Notice we have 7 here, we have 3 right there, so let's get rid of those 3. And then we're left with a total of 4 waters in this reaction. Okay, what's next? Hydrogen ions. How many do we have? 6 over there, 14 over here. We can get rid of all of these, right? Awesome. And then this time, get rid of the 14. And we're just left with 8. 8 hydrogen ions. Anything else that we can cancel? No, we've covered the gamut. Let's go ahead and consolidate our reaction and see what we're working with. I'll say 8 hydrogen ions plus the dichromate ion plus 3 C2H4O yields 2 chromium 3 ions plus 4 waters plus 3 acetic acids, and that is it, right? Absolutely. Do we need to bring anything down? No. Every element is accounted for down here. Now let's make sure that it truly is a balanced redox reaction. Let's go after metals. The chromium, 2 and 2. That's good. Non-metals, carbon, 2 times 3 is 6. Over here we have 3 carbons and another 3 carbons for a total of 6. Carbon's taken care of. Now what about the hydrogens? Here we have 4 times 3 is 12 plus 8. So you're looking at 20 hydrogen ions or 20 hydrogens in total on the left. Let's figure out what we're working with here. Be very careful. Here we have 3 times 3 is 9. But don't forget about this hydrogen. Here's an additional 3. So we're looking at 12 plus 8. So 12 plus 8, again 20. 20 hydrogens, 20 hydrogens. This whole redox reaction is now officially balanced. Now here's an element that you're probably not really accustomed to working with. What is RU? Find it on the periodic table. And as you can see, if you look at period 5, that we're working with ruthenium. So ruthenium reacting with chloride ion plus nitrate ion to yield some type of ionic compound. Notice it's an ion though in the end because we have a net -3 charge. And then nitrogen dioxide. Okay, so let's go for it and calculate our oxidation numbers. Now, since ruthenium is just elemental, it's 0. Okay, the chloride -1. This oxygen, -2, there are 3 of them, so an overall -6 charge. The nitrate ion has a net of -1, so this nitrogen must be a +5. All right? What's going on over here? The chlorines are -1. There are 6 of them, so overall -6. However, we need to keep in mind that we need a net of -3. So what does that say about this ruthenium? It means that it's +3. +3, okay? And then over here, -2, there are 4 of them, so this nitrogen now has a +4. Okay, let's identify what occurred. What happened to the ruthenium? It became more positive, meaning its electrons were stripped away. So therefore, it was oxidized. Oxidized. Okay? The chlorine's okay. It's just -1 on both sides. What about the nitrogen? Here it was +5, and now it's +4. So there was a change that occurred. It became less positive. It gained electrons, and therefore we say it got reduced, okay? All right, let's dive in. Let's do our reduction reaction first. Reduction, okay? We're working with the nitrate ion. And the very first thing that we want to make sure is that the individual nitrogens are balanced. And they are. It's just 1 to 1, no problem. Next step concerns their charges. Here it's +5, here it's +4. So we got to add electrons to the left, right? How many? Just 1. A singular electron, okay, no problem. Now we will focus on the oxygens. Notice we have 2 on the right, but 3 on the left, so we need to add 1 water. But in doing so, what have I done? I've added hydrogens, right? 2 hydrogens. And yes, I didn't need that coefficient there, it's an implied one. So let's add 2 hydrogen ions here to the left. So there's the nitrate, nitrogen dioxide plus the water. Okay, so that half reaction is done. Let's focus on the oxidation here. Oxidation. And it was the ruthenium to form this ruthenium 3 chloride ion. -3, okay? Make sure that the rutheniums are balanced, and they are. Now, which ruthenium is more positive? Obviously this one, +3. So we got to add 3 electrons to this side. Okay? Are there any oxygens that we need to really worry about? No. So we're not going to add waters, and we're not going to add hydrogen ions to our oxidation half reaction. So what we can do now is really just focus on the electrons. So let's do that. So I have 3 electrons over there and 1 over here, so all I need to really do is multiply this whole half reaction by 3. And I'm going to bring it over here and just put it under. 3 times 2, we're looking at 6 hydrogen ions. Now we have 3 times 1 electrons, so 3 electrons, and that's what we were looking for. 3 nitrate ions to yield 3 nitrogen dioxides and 3 waters, okay? All right, let's get into canceling here. Let's get rid of some of these electrons. 3 electrons cancels 3 electrons. Awesome. Now for the waters. Well, there's a problem there. Only our reduction reaction did we have to incorporate water. So we can't cancel any waters. We cannot cancel any hydrogen ions. We're now at the stage where we can consolidate the reaction. So yeah, I'll go ahead and do that. We'll say ruthenium plus 6 hydrogen ions plus 3 nitrate ions yields this ruthenium 3 chloride ion plus 3 nitrogen dioxides plus 3 water. Okay. The next step would be to go back to our original reaction and bring down any spectators. And we definitely have spectators. Notice chloride. So what's going to happen? Those chlorides are going to actually bond with the hydrogen ions to form hydrochloric acid. So let's do it. Ruthenium plus 6 HCl plus the 3 nitrates yields ruthenium 3 chloride ion plus 3 nitrogen dioxide plus 3 water. Okay, it's looking pretty good. Now the final step is to ensure that all is balanced, right? So let's go for it. Just the metals. 1 ruthenium, 1 ruthenium. Non-metals, 6 chlorine. Notice 6 chlorine here. 3 nitrogen, 3 nitrogen. Now we're ready for hydrogens. We have 6 hydrogens here on the left, and over here on the right we have 2 times 3. That's 6. And then last but not least, the oxygens. We have 3 times 3 is 9. And then over here we have 2 times 3 is 6, plus 3 is also 9. So the oxygens are now balanced, and this entire redox reaction is balanced, and we're good to go. So next we'll move into balancing redox reactions in a basic solution.